So guys, today we are going to start with the bracing design. So bracing is a very, you can say, well familiar component of any structure, and you may be familiar with that. So today we are just going to be do a certain design and its types, how depending upon its connection and providing the stability and strength to the structure, how the bracings can be categorized into different types, and how you can use the design parameter as an area of the bracing you can calculate depending upon which factors. So today we are going to be design a bracing for a steel frame. So for the bracing design, you are going to be have a certain knowledge already with that is with you. The bracing in the steel structures are used to reduce the effective lengths of the columns, to reduce the unbraced lengths of the beam, and to provide the overall stability. So if we talk about the columns, so this steel, these braces, those of course be made up of steel. First of all, the sections, which type of the sections you can use for the braces. You can use a simple steel rod for the bracing purpose. You can use the channel sections for the bracing purpose. You can use the eye sections for the bracing purpose, and you can use the angle section also. Okay, these are the most, you can say, commonly used different type of the sections, and out of these also the channel and the rod section is the most commonly used for the steel frames, but still you can use the eye section and you can use the angle section. Okay, so these are the various type of the structures. So for all these you need the area of the brace, that will be the design parameter we are going to be calculate today, and depending upon the area of the brace, that's already going to be depend on different factors and parameters we will discuss over here. And then finally we can get the for the rod kind of bracing. In rod bracing, simple diameter is required, so from the area of the brace you can calculate the dia, and that dia of that particular steel strength, yield strength, is given to you, and according to that steel strength you are going to be provide the steel for the bracing. And for the channel section also, if the area is given, then you can go towards the channel sections tables in LRFD manuals, and then you can find out which channel section is nearly going to give you equal or greater than the area of the brace required, and similarly for the W and the angle section. So for the columns we talk about, in the design of the columns, we have going to be reduced the effective length, and many times we are going to be find out the effective length factor. This effective length factor, and once we are going to be reducing the unbraced length of the column, then we also going to be using only the analytical parameters to describe about its stability and to describe about its strength if we are going to be reducing the unbraced length of any column. But how we are doing this practically, today we will discuss. We are providing the bracing for that. Okay, once we say that we want to reduce the effective length of any column, then you need a proper bracing design for that. The bracings are the word, or you can say the structural components in a steel frames, in although I mean any type of the structure that is going to be used to reduce the effective length of columns. If we talk about the beams, then the unbraced lengths of the beam, those can be provided, or that can be reduced by providing the bracings within the beams. Like your frames, we also have designed a frame in which it's one way, okay, and in the back side, in the lateral direction, you have another frame. These frames needed to be braced. So what you are providing for the bracing system, if one frame is there, okay, and you have already only designed this beam, okay, so how to connect your one frame with the other frame? That is due to with the help of purlins. Purlins are the beams that you are providing. So what actually these purlins are doing, these are providing for the bracing. Those are reducing the unbraced length for this particular beam. When you are going to be designing the main girder, then you have to consider the unbraced lengths for the beam by considering the purlin distance on which those are going to be placed over the beam. Then further, these purlins in the horizontal plane at the roof of your steel frame can be further braced by providing the diagonal or the horizontal bracings. These purlins can further be braced, can further be you can reduce the unbraced length of these beams as purlins by providing the bracing system in the plane, in the roof plane, horizontal plane of your steel frames. Okay, so finally what you are getting, you are providing the overall stability of the whole structure in which the beams and columns are the structural components mainly. So you can provide the bracings for the columns. These may be horizontal braced, your columns can be braced, and the frame can be braced by providing the longitudinal bracings. Those may be braced by providing the diagonal bracings. So any kind of the brace you can provide just to be reduce the ineffective length of the columns and to reduce the unbraced length of the beams and to provide the overall stability. Then you have the discussion on the columns. Once we have done the discussions on the column in the column chapter, whatever the discussions we have done in which those discussions showed how braces could be effective in reducing the effective length and thereby increasing the column strength. Not only we are reducing the effective length by providing the bracings, but on the other side, we are also increasing the strength of the structural component. So as you are, if you remember, the elastic critical buckling load, PE, once you are calculating. So in that particular formula, you are incorporating the K factor. Okay. So this K factor is related with the, is a basic parameter or the factor that is affecting the strength of the column. If you are going to be change the K factor, mean you are going to be increase or decrease the effective length factor, then you are going to be also has an effect on the strength, overall strength of the column or the structure member. So and similarly for the beam design, that beam design you have done in chapter number 4 of your reference book by Dr. Zaid Ahmed Siddiqui that demonstrated how the unbraced lengths of the beam influenced its strength. Okay, so strength is also going to be incorporated in column and the beam designs once we are going to be reducing unbraced length. So how in the beam chapter, you have also calculated, you are calculating the moment capacities for the beams. Okay, so MU, that MN, sorry. So that moment capacity can be calculated incorporating the different factors. You may have LB, you may have LP, you may have LR, and depending upon those unbraced lengths of the beams, you are getting the different formulae for calculating the moment capacities. So your moment capacities are later on dependent on the unbraced lengths of the beams. Okay, so in this way, the effective length factor is affecting the strength of the columns, and the LB mean unbraced lengths of the beams are affecting the moment capacities. Okay, so strength is also going to be dependent on the unbraced lengths for the beam and the by reducing the effective lengths for the columns. And while designing the beam columns that you have done now, okay, and you are also seen this vector moment capacity by considering your beam column as a beam and the effective length factor by considering your beam column as a column. So once you were calculating the PC, mean moment magnification factors and other things, then this PE was involved over there. Okay, so strengths are also involved to be affecting the beam column strengths. And similarly, if you are applying the checks, you are calculating the moment capacities to use the interaction equations for the beam column design. There you need the strength factors also, mean moment capacities also. Those are going to be depending on the effective length factors and similarly on the bracings design of your steel frame. Now, type of the braces. Now we are going to be discussed. Majorly, we are going to be observe within the steel frames the two types of the braces, nodal braces and the relative braces. Here in the figure number 1, you can see on the right hand side the type of the frame. The frame will be the same for both right and left figures, but the type of the bracing is different. So for the right hand side figure, you can see the dotted line, this dashed line. This is going to show you the bracing type, that is the nodal type of the bracing. So nodal type of bracing have certain conditions. Okay, the sections may be anyone, I have told you, maybe rod section, maybe channel section, maybe simple I columns. Okay, but the type depends upon the different end conditions. So for the nodal braces are the braces, those are going to control the movement of a point on the member, mean on the frame itself, the member that is a part of the frame itself, without interaction with any adjacent braced points, any other braced points. Then where it is going to be connected. So what does it mean? That your nodal brace on one side is going to be having a connection with the frame itself or with the part of the frame that required a bracing, that required stability. And what about the other end of this brace? That is going to be connected with the rigid connection, any rigid connection that may be not a part of your frame itself. Okay, or it not be the point, maybe a part of the frame, but it will not be the point that is required the bracing. So okay, so it should not be the point that is required a bracing. Okay, so any adjacent braced point are not going to give you any interaction or end conditions for the nodal brace. Then what should be at the other end of the brace? One end is clear, that is going to be connected for the frame itself or the member that is required bracing. Now what about the other end? The other end for these braces would be attached to the member and then to a fixed support on the other side, such as the abutments as shown in the figure. इस फिगर में आपको जो abutments नजर आ रही है, here you can see the rigid abutments. Any other fixed support or the rigid support is required that is not a part of your frame itself. Your frame is this one. There, this is the column system, all of the columns in continuations, and inside are the beams. Okay, so one part at that particular story, you are providing the stability, you need a stability, and you are providing a nodal brace that is connected on one side with the frame itself. That member is required at that particular, that frame is required bracing at that particular point, that at point C, that at point D, and of course at that point it's continued and downward and upward. Okay, so here you are providing the nodal braces, but for the nodal brace, second end needed to be connected with a rigid connection, and that rigid connection may or may not be the part of your frame. Okay, let's suppose that frame, I mean that nodal brace is like this. That is of your column. हम यहाँ से इसको continue कर लेते हैं. ये आपका बिल्कुल first story है. So here you have the fixed connection, rigid connections. Okay, so this is the particular case, and you are providing a nodal brace like this, I mean diagonally. This is horizontal. This nodal brace may be vertical. You can provide a nodal brace vertical with the same condition that on one side it needed to be provided the bracing system, and on the other side any other system needed to be provided that may be rigid or the fixed. Okay, that should not going to be provided a braced practically for the steel frame itself. So I was talking about this diagonal brace. So let's suppose if we are providing our brace in a diagonal form, then that particular end is connected with the frame that required bracing, and the other end is going to be connected with a fixed connection. So that is also a kind of a nodal brace. Okay, so what you have to be, suppose you have to just justify or satisfy this condition for the definition of your nodal brace, then any, you can say, orientation be okay. For your nodal brace, it may be diagonal, it may be horizontal, it may be vertical. For the relative brace, reverse of that, the definition is just reverse of that. It is going to be, this brace is going to rely on the other brace points for both at both ends of it, of the structure to provide the support. A diagonal brace within a frame would be a relative brace as shown in the figure number 1. In this case, the diagonal brace and the horizontal strut together compose the relative brace. So here you can see in the figure left hand side, these dotted line, dashed line is going to show you the relative brace. Okay, these are the struts, mean the horizontal beams inside of your steel frame. So this is going to give you the bracing on, this is also a brace point, this is also a brace point. So at both ends of it, you are going to be having a brace points, and finally you are getting the two, you can say, points, those are braced within the frame. So there is no rigid connection on either point, either ends. So this is a relative. The relative also may be vertical, may be horizontal. So if these are the two bracing points and these are the two braced points for the stability of this frame, then this is also be a relative, this is also be a relative. We are not providing the rigid connection at the end. So the brace requirement, finally we are concluding our statements. The brace requirements of the specifications are intended to enable the members being designed to reach their maximum strength based on the length between the bracing points at an effective length factor K is equal to 1. That's what we have discussed. So finally what we can conclude, that the brace has the basic two requirements, strength and the stiffness, that you need to be keep in your mind. You have to remember all the time that your brace needed to be, if you are designing a brace, then these two requirements should be satisfied, the strength and the stiffness of the brace. The stiffness means the stability, and strength of the member. A brace that is inadequate in either of these respects is not sufficient to enable the members to perform its function as it was designed. So you have to be very careful while designing the brace regarding these two design parameters. So these are the basically design parameters, strength and stability. So if we go towards the AISC specifications for the bracing design and keeping these two factors in our mind, then the column braces can be designed by using the relative brace. Type of the brace is relative and you are providing for the column. Then the required brace strength can be calculated by using this formula. 0.004 of PR. PR is actually this is the required strength for AST and in AST or LRFT, any you are using the method, but it is a required strength for the member for which you are providing the bracing. Okay, so the column that is needed the brace to be braced. So you are providing the column, and here let's suppose the relative brace you are providing any in between or like this. Okay, from one end of the column or in between of the columns you are providing the relative brace. So it may be horizontal. I have told you it may be vertical or inclined. So in this particular way, let's suppose this column is needed to be braced. Okay, from the top, from in between anywhere. Okay, so this is going to give you the PR, mean the strength of the column, required strength of the column. Okay, and this PBR is the strength of the brace that needed to be designed. So PBR is equal to 0.004 of the PR. Mean this 4% of the strength out of the column needed to be transferred within the brace system. Okay, not more than that. So ये limit है हमारी ASC specifications की कि आप just 0.004 of the PR can be considered as the strength of the brace. More than that is not needed to be transferred because it is going to affect the efficiency of the column itself. Then the required brace stiffness, second criteria. First criteria was the strength, second is the stiffness. So for the stiffness point of view, the required brace stiffness can be calculated as beta BR, that will be 1/5 2PR over LB in LRFT and beta BR omega 2PR over LB in AST. So phi is 0.75 in LRFT and omega is 2 in AST. Keep these equations to be memorized or to be with you. Now, again, continuing the column bracing, but this column is nodal brace. The type of the brace has been changed now. So PBR is equal to 0.01 PR. So 1% of it, so 10% of it. ठीक है? So इस केस में nodal bracing में जो है वो 10% required है कि आपने shift करना है, transfer करना है as strength of the brace. Required brace stiffness, again the formula is given 1/5 8 PR over LB, and here 8 PR over LB same, but here you are using omega. So omega is 2 in AST and 0.75 in LRFT. So here LB is the distance between the brace and PR is the required strength for AST and LRFT. That LB definition is same for the relative brace. In the last slide, I have missed those definitions. In slide number 5, the definition will remain same. Where LB is the distance between the braces, mean unbraced length of the column. You have to consider as LB. Then come the beam bracing, the beam relative brace. The required brace strength is PBR 0.008 MRCD over H nod. This formula is for the beam. Okay, and for the beam, the relative type of the brace, if needed to be designed, then strength, required brace strength can be calculated by using this formula. So within this formula, what is MR? MR is the required flexure strength of the beam. What is CD? Here, this CD is 1 for the single curvature and 2 for the double curvature. This is for the beam. Okay, so if the beam curvature is single curvature, because once you are providing the bracing, then according to the movements within the beam, it can also produce the curvatures in the form of the single curvature, okay, or in the form of double curvature. So if double curvature will be there, you are getting 2, and if it is single curvature, you are taking CD as 1. And what about H nod? This H nod is the distance between the flange centroids. Okay, so from top to bottom. So between the depth of the web, okay, so center of the flange you need to consider till the center of that. That is the H nod. So if this is the case, then you can calculate PBR, strength of the brace, very easily. The required brace stiffness. The formula is given. It is also going to be incorporating the same parameters. CD, H nod, LB, and LB, the definition is same. It is the laterally unbraced length. Of course, your beam is like this. So in the lateral direction, like purlins. So this is going to give you LB. Okay, so unbraced length of the beam. So it will be in lateral direction, unbraced length of the beam. Then comes beam nodal brace. So for that, again, the formula is given 0.02 mR CT over H naught. So you can see for the nodal brace, the percentage of the movement capacity, and for the column also the PR of it, it is transferring is more. Nodal brace के लिए ज़्यादा value हम shift कर रहे हैं brace में, ठीक है? और relative के लिए हम काम कर रहे हैं. Why? Because the relative brace, it's very simple thing, is going to be connected between the 2 points. So the relative brace is going to be transferred from the column. So half mean half, any percentage from one member, and certain percentage is also going to be incorporating from the other member. So from one side, if you are considering a certain percentage of the column strength that is needed to be shifted inside the brace, then from the other side, the other end is also responsible to shifting or transferring the strength from the other side. Similarly, the stiffness. So दोनों साइड से आपके पास आ रही है, जबकि आपके पास जो नोडल ब्रेस है उसमें जस्ट वन साइड इज रिस्पॉन्सिबल. सो यही जो एक एंड है जो आप डिजाइन कर रहे हैं वहीं सारी स्ट्रेंथ आनी है. सो इसलिए नोडल ब्रेस के लिए ज्यादा परसेंटेज रिक्वायर्ड है. द रिक्वायर्ड ब्रेस स्टिफनेस is beta VR and the formula is given. The definitions are same. So frame bracing and column bracings are accomplished by the same relative and the nodal braces, and they use the same stiffness and the strength equations that we have discussed earlier. Now we are going to solve one example problem. So design problem is very simple. So the very basic thing is just to be perceive the problem statement. So for that you have to be focused on the input parameter. You are using the LRFD requirements. If it will be AST, then the equations will be changed as we have discussed earlier. Okay, AST के लिए आपकी equation जो है वो change हो जाएगी, stiffness के लिए particularly, strength के लिए same रहेगी. So if the LRFD requirements are used, then you have to select a rod. So the type of the section, it also be given to you. If not, then any type of the section you can select by yourself. ठीक है, अगर ब्रेसिंग डिजाइन आपको आ जाती है, ठीक है, तो आप कोई भी जो है वो चूज कर सकते हैं. आपके स्टील फ्रेम के डिजाइन में भी आपको ब्रेसिंग के लिए सेक्शन नहीं बताया हुआ, ठीक है, कि आपने चैनल सेक्शन लेना है या आपने रॉड लेना है या आपने किस पर डिजाइन करना है. ठीक है, हाँ, आपकी जो डॉक्टर जाहिद अहमद सिद्दीकी की बुक है उसमें हमारी जो एक एग्जांपल 10.6 सॉल्व हुई हुई है, उसमें उन्होंने जो ब्रेस डिजाइन की हुई है वो चैनल सेक्शन पे की हुई है. आप उसको अगर पूरा देखें तो उसमें उन्होंने ब्रेसिंग जो है वो चैनल सेक्शन से दी हुई है, जो हमने लॉन्गिट्यूडनल ब्रेस देनी है लेटरल डायरेक्शन में. ठीक है, आपको मैंने प्रॉब्लम स्टेटमेंट में समझाया था, आप लोगों ने भी डिजाइन करनी है. सो उसके लिए जो उन्होंने दी हुई है वो चैनल सेक्शन डिजाइन किया हुआ है. सो अगर आप उसी को फॉलो करना चाहते हैं अपनी एग्जांपल नंबर 10.6 को, तो उसके अकॉर्डिंगली आप उसी को फॉलो कर लें और चैनल सेक्शन निकाल लें. ठीक है, अगर नहीं तो फिर आप जो है रॉड निकालें, बट द फॉर्मूला विल रिमेन सेम. जस्ट ABR तक जो आपने फॉर्मूला लेना है वो डिफरेंट होगा कि आप ABR कैसे निकालेंगे, एरिया ऑफ द ब्रेस आप कैसे कैलकुलेट करेंगे, रेस्ट विल रिमेन सेम. ठीक है, सो rod, let's suppose in this particular example we are using the rod to provide the nodal bracing. So type of the bracing is also given. ठीक है जी, आप nodal brace provide कर रहे हैं, shown in the figure number 2, to resist a wind load of 18 kilonewtons and provide the stability for a gravity load of 500 kilonewtons and live load of 200 kilonewtons. So 3 type of the loads are needed to be resisted by providing the bracing system in the form of nodal bracing, and the shape and the location is given in the figure. This figure number 2 you can see. This figure number 2 is going to show you a frame that is having the 3 bay frame. ये front side है frame की, ठीक है. So we are not interested in the connections and all other things. Okay, and in the lateral direction it's another frame. Lateral direction में एक और frame है आपके पास, ठीक है जी. So whatever the bracing you are providing in the lateral direction, we are not concerned. Our concern is not this one. Our concern is with this nodal brace. That nodal brace in the frame that is going to be provided in diagonal form. Okay, so this is one nodal frame, and for the reversal of the load cases we are providing, for the diagonal always we are providing another brace in the other direction, equal and opposite, with the same theta. Okay, so this will be the angle of the inclination for the brace, theta. That will be the same for both sides. Okay, so you are providing the proper connection over here, rigid connection. Okay, so that rigid connection is going to satisfy the nodal brace conditions. So also it is written it's nodal, so it will be obvious that it is going to be having a rigid connection. This end is the brace point for your nodal brace. Okay, so here also this is the brace point for the other, and this is the rigid connection. So in this way you are going to be having a nodal brace that is diagonally placed within the frame. And the length of the column is 4.87 meters, 16 feet. And the bay length is 30 feet, that is 9.14 meters. So for this particular frame inside this bay, you have to design your nodal brace. And of course, in the back side, lateral direction, it's 15.24, the distance between the frames in lateral direction. So step number 1, in steps we are going to be design it. So the same steps you have to follow for your case also. Once you are designing your any problem statements for your assignment purpose or for your designing a steel frame. You have to determine the required brace stiffness for the gravity loads. PR is simple formula, that's 920 kilonewtons. Keep this PR with you and you can find out the stiffness of the brace. Design stiffness, you can write. इसको आप जो है वो simple जो है वो separate out करेंगे, that based on the design LRFT. Okay, so by inputting all of the values, you have PR, you have the LB for the member itself, that is column. It's column bracing. So 1 over 0.75, 8 into 920, load 4.87. You are getting this 2015 kilonewton per meter. Keep the stiffness value with you. Okay. Now step number 2, you need to determine the required brace area, accounting for the angle of the brace. That is actually the last step, mean only 2 steps are required over here. So the area of the brace can be calculated by the strength criteria. स्टिफनेस से आपने ये कैलकुलेट, एक डिजाइन स्टिफनेस आपने ले लिया, स्ट्रेंथ क्राइटेरिया को यूज करते हुए आप जो है वो लोड निकालेंगे और उस लोड से आप स्टिफनेस का फॉर्मूला निकालेंगे और उससे करस्पॉन्डिंगली आप दो स्टिफनेस को जो है वो डिजाइन और अवेलेबल stiffness for the brace आप इसको कंपेयर करेंगे और वहां से आप एरिया ऑफ ब्रेस कैलकुलेट करेंगे. So see how we are going to do that. Step number 2, you have to determine the required brace area accounting for the angle of the brace. Okay, so if it will not be there, then directly you can calculate by using the strength equation, the load equation, but here the angle is incorporated because your nodal brace is at an angle as an inclination. So that is going to be give a certain complication. I mean, now your load is not in the same direction as the delta is there. If the horizontal loads has been provided, mean the lateral loads has been observed, going to be experienced by this frame, then the lateral deflections be there. So due to these lateral deflections, your column is going to be deflect like this. Your brace is required to be provide enough stiffness and the strength so that it can come back to its original position. It is not going to give you the sway conditions. So you are need to provide the stability. So this delta is in lateral direction, but the load in the bracing is not in the horizontal direction. If it is a tensile force, then this load is in this direction. So if you are going to be consider the strength criteria, mean a second, you are calculating the load in the bracing, it will not be the same as you have calculated the stiffness in the lateral direction. So what you have to do, we have to do a certain transformation with respect to theta angle inclination, and then we will be able to calculate our required, or can compare our stiffnesses and we can calculate the area of the brace. So this slide number 12 is regarding that particular transformation of your deflections and your loads. So the step is same. You have to determine the required brace area accounting for the angle of the brace. Now, when the cross bracing is used diagonally, it is generally assumed to be effective in tension. That's very obvious. Once you were designing the roof truss and any truss you were designing, so that you have discussed over there, that those members you are providing diagonally in the trusses also as in compression member. So for reversal of the cases, once those will be in compression, those will be ineffective. When those will be in tension, then you have to be designed very carefully. The same design you are designing in reversal cases in tension, the same you can provide in compression. Why? Because the diagonal that is in compression, due to its longer length, buckles a little and becomes ineffective. Okay, so it's not going to be make any problem in compression, but in tension it is going to be make, because the increase in the length happens. In compression, it is the buckling be there. Okay, but in tension, the increase in length be there. So whatever the case is, if movements be there, loads be there, then in tension, your bracing are more effective and needed to be designed. So whatever the design in tension you are doing, the same area of the brace you can provide in compression also. For the horizontal movement of the delta shown in the figure number 3, elongation in the brace is delta cos of theta, and the strain produced is delta cos of theta divided by LPR. Now that is the same factor. Once you are providing the going to be apply the lateral loads, these lateral loads are going to be give a lateral response for the frame will be deflection in the lateral direction. It will be delta. If you want to transform this deflection in the direction of the brace itself, then you need the component of the delta in the same direction. This component of the delta, the lateral deflection in the direction of the brace itself, will be the delta cos of theta. The angle is theta. The same angle is going to be formed with this component and the delta. It is delta. This is theta. And here this component will be delta cos of theta. Cos component of it. So this is resulted. It will be delta. And it will be delta cos of theta. So magnitude wise, if the loads be there, then you can show arrows, okay, but not because it is the vector. It is a vector, so I am going to be show the arrows also, but it is delta. So just the magnitude we are requiring over here. So for the magnitude point of view, you are transforming your delta lateral deflection in the direction or in aligning with the brace itself. So it will be in the direction of the brace. It will be delta cos of theta. If this is the deflection along the brace, then this delta cos of theta is the deflection. How you can get the strains out of it? For the strain, you are calculating delta cos of theta divided by LBR. Of course, the change in length divided by original length. This is the strain. Why we need a strain? That is the question. Why we need strain to be calculated over here? You are familiar with the formula or the relationship, that is stress is equal to E into strain. Okay. Now, if we are going to be replace your stresses with P over A, here A is area of the bracing, capital E will remain same, and E with the change in length divided by original length. That will be area of length of the brace. L naught if we talk about that. Okay. So here the strain comes. And what is the definition of the stiffness? If we talk about what is stiffness actually, your stiffness is equal to P over, or the relationship between P and strains, mean delta. Okay, strains itself. So if we want to calculate the stiffness, then we need this formula. This is the rate of change of strain with respect to load. So in this equation of stress and strain, we can replace, and the relationship between the P and the strains can give you, mean P over delta can give you, not the strain, delta. P over delta can give you the change in strain, change in length can give you the stiffness value. Similar we are doing over here. Now, once the strains has been calculated, then what you can calculate, you can calculate the force in the brace. That will be equal to ABR EBR over LBR into delta cos of theta. So what does it mean? With this, by continuing this equation, you can keep your P on one side, and on the other side you may have E into A into delta L over L. So just input your values. A as ABR, L as LBR, length of the brace, and delta L, change in length, is delta cos of theta. So what you can do, you can just input the corresponding values in it. Now, next is the corresponding spring constant then becomes. So we need only the relationship between P and delta. Okay. If we are going to be develop a relationship between P from left hand side of the equation and delta on the other side of the equation, then discluding the delta, all other parameters will be the spring constant, mean beta. It will be equal to the stiffness, mean beta. So beta will be P over delta. Okay. So the spring constant of this equation, the constant of this equation will be E ABR cos of theta divided by LBR. Okay. So it will be this one, ABR EBR LBR into delta. So force you can calculate like this. And the component of this force acting as resisting shear in the horizontal direction evaluates as like this, y delta cos theta square. Okay. So how you get this square? Now, this delta that you have already been calculated, this is in the direction of the brace. Okay. And by using this delta cos of theta, you have calculated the P, mean the force that is in the direction of the brace. This is in direction of brace. Okay, mean inclined. This is P you have calculated. Now, if you required the P, mean the bracing system you are designing for the frame itself, then the strength of the frame is required in the direction of the deflection, lateral deflection. It is not required. The frame stability and the frame strength is not required in the direction of the frame, the brace. It is required in the direction of the deflection, lateral deflection. Mean you need to be transformed your force again in the direction of the lateral deflection of the frame itself, not in the direction of the brace. So the brace force now can be calculated. The component of it can be calculated in the direction of lateral deflection of the frame. So it will be again, your load is going to be transformed into its components, and its component will be P cos of theta. Okay. So here you are calculating component of the force, again shifting on in the lateral direction. Okay. So two frames mean two axes of the system. Axis system we have discussed. One axis system is in the direction of delta, and one axis system in the direction of the brace. So first delta is in the lateral direction. We have calculated the component of the delta in the direction of the brace. From this component we have calculated the force in the direction of the brace. And then we have shifted this force in the direction of the brace in the direction of delta. Okay. So this P cos of theta will be the component of the force in the direction of the actual deflection of the frame in the lateral direction. So in this way it will be cos square comes, rest will remain same. So this cos square theta now will be, mean cos theta whole square will be going to be incorporating to calculate the spring constant, mean constant of this equation. That is going to be develop a relationship between P and delta. So rest all of the parameters will be going to be represent you the stiffness of the brace available within the frame, depending upon the available situation, the required situation of your delta. Okay, so this you can say this is the beta by the step number 2 you have calculated. This is the available stiffness of the brace, and that is needed to be compared with the design stiffness of the brace. Designed you have calculated in step number 1. Okay, so the available and designed should be equal to each other. So if you are going to do that, then this was the design stiffness answer 2015, and on the other side you have calculated this spring constant ABR EBR over LBR cos square theta. So based on geometry of the frame from the figure, theta can be calculated. This and you can incorporate over here. This result is the required brace area. Here in this equation, if you are going to be equate your designed and available, this is your available stiffness and this is your designed stiffness. Step number 1, step number 2. This is by step number 1. This is by step number 2. Now in step number step number 2 continuing. ठीक है, so इसी step में हम इसको equate करेंगे. Here the area of the brace is unknown. Okay, so you can take out your area of brace and rest you can input all of the values LBR, theta, and you can get the area of the brace. That is going to give you answer 133.74. Keep this with you. This area of the brace is based on stiffness. Based on stiffness. 2 criteria we have to follow. Keep this with you. This will be your ABR1 based on stiffness. Second is in step number 3, you have to determine the required force for the gravity load and for the wind load. Okay, so depending upon strength. So for the strength point of view, we have already the formula. So horizontal brace for the nodal brace equation is with us, that is 0.01 PR. So PR depending upon the gravity load, it is different. and PR depending upon the wind load, it will be different. So what we have to do, we have to calculate separately for to calculate the strength of the PBR, the with respect to gravity load and with respect to the wind load, and finally we can combine both, okay, to get the final answer for this, for the strength, for the load within the bracing, which gives a force in the member bracing. This is 9.2 cos of theta. Okay, so you have 9.2, that is the force PBR. But actually, whatever the force we have calculated, this is 9.2. This is in the lateral direction. Okay, so what we have to do, we have to consider in the direction of the brace. So we have to take cos of theta. Okay, so आप इसको divide करेंगे, that is going to give you 10.42. So ABR is equal to 46.31. Keep it this with. Step number 4, for gravity plus wind load, determine the stiffness and the strength requirement. The stiffness requirement will be the same as the step number 2, but the strength must be sufficient to resist the 18 kilonewton wind load. So separately 1.3 is the factor, 18 is the load, and cos 28 is the cos of theta, that is to be converted in the direction of the brace, and 0.9 to 50 is the factor, and 250 is the yield strength. So you are getting 117.78 millimeters square. Okay, so what you can do now in step number 5, you can add due to the gravity load and due to the wind loads. So both of the effects are summing up, superimposed, both of the effects, and finally you are getting your area of the required. This is 164.09. Okay, so now this will be the area of the brace depending upon strength, load. Okay, so this will be 2. So out of these two, the larger one, 164.01 will be the final, because last time we have calculated it was 133.74. So out of these two, depending upon stiffness and the area and the strength, the larger one is going to be select. You can select. This will be 164.09. So corresponding to 164.09, you can calculate dia and you can round it up to the maximum side. So if it will be a channel section, then you can go towards the channel section tables, and from there you can select. If it is an angle section, then the lighter section you can select, and you can go for the required area. Required area. Okay, so this is it for your bracing system. जी गाइस, आपकी रिकॉर्डिंग मैं एंड कर रही हूँ.